All right, let's test that understanding. Here we go. So suppose a 20 kilogram box lies at rest. Okay, so already we're seeing some important stuff happening. Sounds like my food's done. Lies at rest. 0. Mass. So this is some kind of velocity. I don't know what kind yet. Leave me alone. On a flat surface with the coefficients of friction. Oh yes, I do. That's going to obviously be our starting. Coefficients of friction are mu s equals 0.8 and mu k equals 0.2. While the box is at rest, an applied force F is exerted on the box to the right for several seconds. A. Suppose F equals 100 newtons. What is the strength of the frictional force? I'm going to peek ahead to B. So what is the strength of the frictional force? What is the strength? We're going to need to find our frictional force. So let's go ahead and do that because we're given two coefficients of friction to begin with. So our static friction, the maximum static friction, remember, is going to be mu s times Fn. Mu s is 0.8, and then Fn is 20 times 10, 200. So our maximum static frictional force, max, equals 160 newtons. Okay, and over here I'm going to do my kinetic friction. Let's see, Fk 0.2, same equation, except we're using mu k times Fn. So we have 0.2 times 200, which is going to give us a frictional force of 40 newtons. All right, I cleaned it up a little bit, so we have our maximum static coefficient of friction, 160 newtons, and our kinetic friction, 40 newtons. Now, part A, what is the strength of the frictional force? Well, it's going to be, is it going to move or not? Well, it depends. So let's first start with a free body diagram to see what's happening. So if we have a box on the ground, we'll start with the easy one, which is our weight force, which is mg, right? So we have the weight force. We have the normal force. It's not sinking. It's not going upwards. We have 100 newtons applied force. However it's applied. So that's the 100. We're going to just say a hand is pushing on it just because it's easier. And our frictional force is going to increase until it matches or cancels out. So our frictional force here is going to cancel out because our applied force, when we start applying the force to it, our frictional force, the maximum static frictional force, is not overcome. So in this instance, our frictional force equals 100 newtons because the maximum static frictional force has not yet been overcome. All right, so what motion does it have? Not moving. Not moving. Is that it? Box stands still. It's not moving. That's it. All right, on to B. Suppose 160 newtons of force. I'm going to go ahead and start with my free body diagram. So it's the same question. We're just changing the amount of force that's being applied. So we're still going to have... That's about right. So we're still going to have Fn and mg, our weight force right here, and Fn right here. Our frictional force is going to, is it overcome yet at 160 newtons? Not overcome yet. So that means our applied force is going to be equal and opposite. These two lengths are going to be equal. So in this instance, we have not yet overcome static friction. It hasn't broken yet. That's how you draw 6, right? Still not moving. All right. Now that we are applying 200 newtons, now we're no longer in static equilibrium. Now our frictional force, at most, is going to be 160 newtons. Meanwhile, our applied force is going to be longer at 200 newtons. So, what is the strength of our frictional force? In this case, it's going to be 40 newtons. But Mr. Scapatis, where did 40 newtons come from? Alright, so we have now reached the maximum static frictional force. We've matched it in part B. And then part C, we've broken that maximum frictional force. And as soon as you break that, then the object is going to begin to slide. So we are now accelerating to the right. I should come up with a shorthand for accelerating based on how long it is and how often we use it. Another day, right? What does the motion have? What motion does it have? It's accelerating to the right. That's not very specific. So instead, we can probably explain how fast we're accelerating to the right. To do that, well, we've got a free body diagram. If we have a free body diagram, we can come up with Newton's second law equation. And Newton's second law equation says the net force is the stuff that makes it go. That's an A, not an N. The stuff that makes it go, the applied force, minus the stuff that holds it back, FF, equals mass times acceleration, the net acceleration. So the applied force is 200 newtons. Frictional force is 40 newtons. That equals 160. Equals mass, which is 20 times A. And we see that A is 8 meters per second squared. So accelerates to the right at 8 meters per second squared. And now I'm going to clean all this stuff up again.